Good day, class. This is the week 15 Wednesday session. We'll review your exam 4 for solutions, and we'll do a final exam review at the end of this session. So the first thing we're going to take a look at is a review of our, well, let's do the final second. Let's look at your exam 4 solution first. This is exam 4 solution. I will tell you this is one of the highest averages I've ever had on a statics exam. The overall average was 27.4 out of 35, which is about 78.5%. There will be no points added to this exam. I'm very pleased with the overall results. I had 4 grades over 100%. The high grade was 40 out of 35. I had a 38 out of 35, and I had a 36 out of 35. So overall class average was one of the highest ever for any exam in any year that I've taught statics. So here, let me run through the solutions with you. Take it down a little bit so we could see it all on one screen. So I want you to do the shear and moment diagrams, and what's important is to show key values. Sometimes you don't show all the values that are important, and these key values occur at the boundaries, okay, the discontinuous boundaries that we have. Looking in particular for the maximum bending moment, that's key. So we have this particular beam, 80 kN load at the far overhang end. We have a 20 kilonewton per meter distributed load. 2 supports at A and B. First thing you do, of course, is solve for your reactions. That's extremely important that you do this and do this correctly as we go through the solutions. And when you do that, you'll find that reaction at A is 230 kilonewtons, and I don't see if I have this posted. There it is, 230 kilonewtons, and the reaction at B is 30. And the reason for this high, you probably imagine this very high reaction at A, is you have this in close proximity, this 80 kilonewton this way. You have the 30 kilonewton per meter beginning to act right over that, okay, which tends to set a moment in the opposite direction, and ends up being most of the load is taken up over here at this particular point, particularly this overhang load that we have. So the first thing we do is we solve for reactions, and you should check to make sure the reactions are correct. Then we want to draw the vertical lines of discontinuity. Not all of you did this. Every time we have a load, so this is the first line, we have the support A, discontinuity, and it's also the beginning of our uniform distributed load. And then at the end of the distributed load, there's a discontinuity at that point also. So we drop a vertical, and of course, at the end of the beam, we vertical, then we do our horizontal shear, kilonewtons plus and minus, moment, kilonewton meters plus and minus, okay, the lines. And then we just go through the technique of drawing our shear diagram. We're dropping. We started 0 at the end of the beam. We're going down 80 kilonewtons, and that's a concentrated load. So it's constant. Shear is constant. It's in the negative direction. And then here at A, this is the support reaction, 230. That's going up, and we're at minus 80 going down. That takes us up to a plus 150 right here. And then we have a distributed load that's going to be decreasing as you go across, negative shear. Okay. And it's acting over 6 meters. 6 times 30 is 180. So it's going to drop ultimately 180 from this 150. This is a function of x, so it's straight line. So 150 positive, it's going to drop 180. 6 times 30, 180. So it takes us down to a negative 30. So we create a straight line down to negative 30. And then it's constant from here on. So this is 30 here. We get at support A, and sure enough, there is our 30 up, and it takes us back to 0. So we started 0, ended 0, sure that our reactions are correct, and so this shear diagram is correct. What we learned is that these moment areas in shear, or these areas in shear, create our moment reactions down here. And we just simply have to calculate these areas. The shear diagram crosses its 0 axis at this point. And we know this point is going to, where shear is 0, it's going to be a, locate the maximum moment. So I want to drop a line here. And I need to know, to calculate these areas, I need to know this distance. Okay, x equal to 5. And so we're at 150. We're dropping 30. We need to go to 0. So I have this little equation. We've talked about this. X, which is how far we have to drop, times 30 should equal 150. And that takes us to this 0 point. And we find out that x is equal to 5. Okay, 5 meters from this point here will give us this 0 point. If this is 5, then and it's 6, then this distance is 1 over here. So we're able to calculate the areas, and we want to keep track of the positive and negative areas. So the first area is the 3 times 80, 240, and it's negative. And we know that moment is a function of x. So we just drop a straight line, decreasing, 240. Okay, 3 times 80 is 240, negative 240. And then we're in this region of uniform distributed load. The maximum is going to occur here. And what I do is I'm just going to freehand, and it's going to, this curve, it's a function of x squared, is going to stop here at the end of this uniform load. So I'm going to just freehand a curve in, max it out here, and then it'll continue to drop here, and I'll calculate these points. Okay, so I have this area up here. There's a triangular area up here. 1/2 base times height. Okay, and so it's 1/2 of the base is 5, the height is 150, and that gives us an area of 375. It's positive. So I have negative 240 plus 375 gives us 135 here. Then this other area is negative area, and that area is 1/2 the base, which is 1 times the height, 30. And this area then is equal to negative 15. So it's decreasing negative 15 from the 135, which takes us down to 120. This rectangular area is negative. Okay, base is 4, height is 30, and it's negative 120. Again, straight line for decreasing for moment. And here we're at 120, this negative 120, straight line down to 0. I know I've done this problem correctly. I started at 0, I ended at 0, and I know, and the reason I know this is a correct problem, I know this is correct up here. Reactions were correct. We were 0, 0 in shear, 0 here, 0 here. Hatched it in. That's the first problem. Second problem, 2 parts. The first part asks us to calculate the shear force in bending moment at x equals 10 feet. Here's 10 feet. I actually showed this on the beam itself. So this is the section we're looking at, section C. There's no x's. It's just a straight calculation, sum of forces in the y and sum of moments. Fairly simple problem. Just be sure you draw your free body diagram. We can do this 2 ways. We could take the section to the right of C, including C, or we could take the section to the left, which would mean we'd have to go all the way out. So I'm going to choose to go to the right. Either one will get you the same answer. In fact, you could do it both ways and check. So I'm just going to go this way with it. So here's my free body diagram. Section C, 2 feet. This is my reaction, 6.4. Here's the face that I cut. This is positive shear, V. This is a positive moment. It's in the clockwise direction. This is how we set it up to begin with. And again, we have this uniform load of 2 kips per foot. This is 2 feet. So there's a 4 kip load right in the center. Really simple, some forces in the Y. We have V minus 2.4 plus 6.4. V is equal to 4 kips. So at that section, shear is 4 kips. We sum moments equal to 0. Okay, this is a positive looking at the section, but when we do the calculations, it's clockwise, counterclockwise. So this is a negative moment, minus m, minus 2.4 times 1, its moment arm, plus 6.4 times its moment arm is 2, equal to 0. So moment is equal to 10.4 kip feet. This is one of the first problems that you encounter in strength of materials. And typically on the first day, when I teach the class, I hand out a sheet that has 5 problems similar to this and say, calculate the shear moment at a particular section. So that's the first thing you're probably going to come into when you get into the strength class is this problem. Okay, the second part, B, is we want to write equations in the section from 3 to 6. So this is the sections from 3 to 6. This is the easiest type of equation you can write. And the reason for that is that you're not involved with any of the uniform distributed loads. So X starts always from the far left of the beam to somewhere in this 3 to 6 section that we have. So here's the section. Okay, over here is the A that we have set up over here. And this reaction at A is 4.8. Okay, that's the reaction here at A. Here's the face that we cut. This is, again, positive shear is down. Moment is counterclockwise at this particular section. And then all we have is this 4-kip force here. Okay, so this distance is X. We need to know the distance between the 4-kip force and the end. So if this is X, and this is 3 feet, this distance must be X minus 3. We've done this several times. Okay, so we sum forces in the Y, the minus or the plus 4.8, this reaction, minus 4 down, and shear is minus, it's in the negative direction, so it's minus V. So shear is equal to 8/10 K. That's the equation for shear anywhere in this section, which means shear is constant. And sure enough, we said it would be constant. This is a concentrated force. So this is the equation for shear. Some of the moments, we just take moments about this cut face, plus M, minus 4.8 times X. So here's the 4.8. The distance to the face is X. So the moment is 4.8 times X. It's in the clockwise direction, so it's minus. And then we have the 4 times its distance is X minus 3. And this is going to be this direction, counterclockwise, so it's positive. So this is plus 4 times X minus 3 equals 0. Combine terms, and you get the moment is equal to 12 plus 8/10 X. So anywhere in this section, you can plug in a value for X, and that is the moment. Okay, so this is going to be a function of X. And that's it. That's all there is to calculating the equations. And in particular, I just chose this section because it's much easier to work with than if you're having a section in here. This is very workable. I mean, it's just keep track of what we did here, but you're using a distributed load. So this force in here would be X, and the distance out would be X. That's where you get X squared. Now let's take a look at the third question. And again, this was a shear in moment diagram. Again, the first thing you do is you calculate reactions at A and B. A sub Y is 24.5 kips, and B sub Y is 15.5 over here. So this 15.5 kips over here. So we have a reaction up. Again, discontinuities, we drop verticals here, discontinuity here with the concentrated load, beginning of the uniform distributed load, discontinuity, so we drop a vertical here. We drop a vertical at the end of this load. Some of you are missing your lines of discontinuity, and that messes everything up for you. And then, of course, at the end. Okay, so those are our vertical lines. Anytime we have a concentrated force, the beginning and end of a uniform distributed force. So we're starting at 0. We're here at the reaction. Reaction there is 24.5. So we go up 24.5. It's constant. Over to this line of discontinuity. 20 kips down, we're at 34.5. Okay. .5, 20 takes us down to 4.5. It's constant here. So we go over to this line of discontinuity. So this is 4.5. So again, okay, we're at 10 feet. We're going to drop 2 kips per foot. So we're going to drop 20. And shear is going to be a function of x. So it's going to be straight line decreasing. We're at 4.5. We drop 20. That's going to take us to 15.5. And so what I'm going to do is use my straight edge and drop the line down to negative 15.5. This will be constant over here to the end where we drop down from B. So we're negative 15.5. Our reaction at B is 15.5. That takes us back up to 0. So we start at 0, end at 0. I know my reactions are correct. I know my shear diagram is correct. Again, we're going to do the same thing. We crossed line for shear, and we're shear for this shear line here crosses this. Shear is 0, and where shear is 0, that's going to be maximum moment. Okay. And so we just do areas, and we need to find this distance again. And so what we're looking at is an equation to do that. And I had this over here. This is 4.5, and we're dropping to 0 with 2 kips per foot. So 4.5 is equal to 2 times x. How far do we have to go to get to 4.5? Which means we'll take 4.5 down to 0. We're subtracting that. And so x then is equal to 2.25 feet. Then this distance here would be 7.75 feet. From that, we can calculate the areas, rectangles, and we have triangles. This first area that we have over here is equal to 98. And this is positive, straight line, function of x. So we start here at 0. We go up to this discontinuity. This is 98. Okay, we go over to the next triangle. That area is going to be 18. It's a rectangle here, sorry. It's 18. We're at 98, add 18 to it, again, straight line, takes us up to 116. And then we're here at the uniform distributed load. We've located where the maximum would be. So this function x squared is going to continue in this section. So what I'm going to do is curve. It's going to peak here. It's going to continue on its curved path down to here. And so what I do is calculate this positive area here. is 5. I'm at 116. So this means this must be 121. And this is absolutely the most important value in a shear moment diagram, because this gives you the maximum moment in the beam. And when you're doing an analysis and design ultimately of a beam, this is one of the parameters, key parameter that you're going to use is the maximum moment. Have to show that. And then we have the larger triangle, which is negative. Okay, that area ends up being equal to 60, negative 60. We're at 121 minus 60 takes us down to 61 again on the curve. And then we have this area out here, which is negative rectangular area. I think I actually calculated this as 62. Sometimes when if you round off some of the decimals, you may be off like 1. Okay, you shouldn't be off more than 1. So this is 61. Sorry, 62. I'm going to call it okay. We just draw the line down here and it ends up being 0. Okay, so we start at 0, end at 0. Key takeaways, your lines of discontinuity, your reactions, the way you treat this, you're going to drop from whatever this value is, you're going to drop 10 feet, 2 kips per foot, you're going to drop 20 from whatever this value is up here. That's how you treat a uniform load. Again, 0, 0, 0, 0, and both shear and moment. And we know this is correct. This is the 4th problem. This was 5 points. We have a packing crate, 150 pounds. It's resting on a floor. We have a horizontal force P pushing this. This is P here. At some height H above the floor, contact surface, the floor with the crate. We want to know how high this force is, what is H, so that the crate will move without tipping. Okay, the friction force is equal to the coefficient of friction, 0.035, times this 150 pounds. Okay, that's the normal force. Okay, N, wrote it here, N is 150, it's equal to the weight. Okay. So the friction force is 52.5. And then I'm going to take moments about A. This would be just basically on the verge of tipping that we're looking at. Minus 2.5, 52.5 times H. Okay. Plus 150 times 1.5. 150 times 1.5. 52.5 times H. And you get H is equal to 4.29 feet. Pretty simple problem, pretty basic problem. Nothing complicated about it. Extra credit problems. There's a block on an inclined plane, and there's a weight attached to this block. And this weight is attached over through a pulley system. Okay, and they're calling this mg. So we want the value of mg in kilograms. that will keep this block from sliding down this plane. Actually, there are two types of problems in this. And the block weighs 100 kilograms, or mass is 100 kilograms. Okay, it's inclined at an angle of 20 degrees. The other type of problem that you can look at is, what does it take to actually move this? How much weight out here, mass, weight, out here at mg, will it take to actually move this up the plane? Okay, so there's one where it's just on the verge of sliding, what it's going to take to keep it from sliding down the plane. And the other problem here, you could work with another problem. What does it take to actually move it up? So you want to overcome friction here, and friction here is going to help keep this in balance going in this direction. So what you do is, I drew the free body diagram. Okay, here is the weight. I did this, I went ahead and converted to newtons to begin with. So I did the 9.881 times 100. So I got, of course, 981 newtons. Okay, so this weighs 981 newtons. And it's at an angle of 20 degrees. So this is 20 degrees here. If this is 20, this is 20 here. So N is going to be acting in this direction, and that's going to be a cosine function. So if it's 981, I need this component, which would be equal to N. So this is adjacent to the 20 degrees. So this is a cosine function. So 981 times the cosine of 20 degrees, N is equal to this, 981 cosine of 20 degrees. So N is equal to 922 newtons. And so the friction is equal to 0.3 times 922 newtons. And so the friction force I got is 277 newtons. And if we're looking at motion this way, we're looking at friction force going to be up, directed up. So that's what I have here, friction directed up, 277. Okay, this is T, call this the tension force, which wraps around the pulley to mg down here. And I just take some forces in the x direction. This is my axis system. This is x direction. So I have plus T plus the 277, which is friction up, minus this weight wanting to take it down this way. And so taking this in this direction is a cosine function. It's opposite. Okay, so it's 981 cosine of 20 degrees equal to 0. You get T then equal to 56.5 newtons. And I went and, you could have just stayed with the kilograms to begin with. I changed it to force just to be using the forces. And so mg then in kilograms is 5.96 kilograms. This extra credit problem is one we did in class. This is belt friction. So we have a 100-kilogram mass. There's some type of belt or rope system around this cylinder. We want to know what this force P is over here. And when we developed it, this force would have been T1, this one would have been T2. That's how I sort of wrote the equation. So T1 is equal to this P force out here. What we want to know is we give the coefficient of friction between the rope and the drum is 0.3. Motion is impending. Calculate the force P that must be applied to keep the weight from slipping downward. And we assume the rope is in contact with half the cylindrical surface. So the equation is T2 is equal to T1 E to the power of mu beta. Mu is the coefficient of friction. E is the base of the natural logarithm. It's equal to 2.718. And beta is the contact angle in radians. There are 2 pi radians in 360 degrees. This is in contact with half of the cylindrical surface. Okay. So beta is pi radians. And so we just put this in this simple equation. 981 T2 is equal to T1 and so on. So T2 is 981 is equal to T1 E to the 0.3 pi power. 981 is equal to T1, and this over here then ends up being 2.57. And so T1 is equal to 382 newtons. And that's equal to P. So P is equal to 382 newtons. Converted up here to begin with. Okay. And several of you got this answer correct. Didn't do this problem in class, but if you fully understand how shear behaves in terms of concentrated forces and uniform distributed forces, some of you were able to do this particular problem. So what I did is I gave you a shear diagram with values. I gave you the outline, the broad outline here. We know where the discontinuities will occur. And I asked you to draw the diagram or the actual beam loading and the beam reactions given this shear diagram. So what I did is I projected lines of discontinuity up. There's one here, this point, and sketch the beam. And I'm starting here at 0, and I go up 25.7. That's got to be a support. Okay, so draw this support, say a pin, and the support reaction is 25.7. It's constant, so nothing is going on here till we get to this discontinuity. And I went from 25.7 down to 5.7. So I dropped 10 kips, which means that I had a concentrated force of 10 kips down. And again, it's going to be constant in this region. This is what happens here. It's constant. And then shear is a function of x, so I know this is a distributed load going from 5.7 down to 18.3. So I'm dropping 24 kips from here to here. Well, I go, well, 24 kips, if this is 6 feet, this distributed load must be 4 kips per foot. And so I draw the distributed load, 4 kips per foot. 6 times 4 is 24. That takes me down to here. It's constant, nothing's going on here. Okay. And this must be the other reaction at this end. 18.3. This reaction must be 18.3. This is my beam. I've actually done this in some classes where if a student wants to try this, and I've had some successful, I actually give them the moment diagram. It gets a little bit trickier. Like I said, here's the moment diagram. Tell me what the beam looks like, and then what they have to do is construct the shear diagram from the moment diagram. And again, you know the relationships, and so they construct this, and then they're able to take this and construct the beam itself. Had some students be able to do that. So that is your exam. Again, no points added. You should have the grades. And so I just have a homework assignment to grade. Everything else will be up to date on Canvas. So let's look at final exam review. And what I'm going to talk about is extremely important. So, and this is posted, it's posted online, but I say some things that aren't written on here. So these are important. So our exam is December 13th. It's actually scheduled to go to 11:20. I'm going to take it to 11:30. So it's 9:30 to 11:30 on December 13th. There'll be 6 problems, 2 to 3 extra credit problems, and I may have extra credit built into one of the 6 problems here. All problems are 10 points each. You can use up to 3 note sheets. I caution you, you don't want to be thumbing through. Well, you'll sort of know where your notes are at for particular problems, but you can use up to 3 note sheets, both sides, 8.5 by 11. Extremely important, your work must be legible in a vertical order. Don't skip around. In other words, you start here and you work your way down. Don't all of a sudden be down here somewhere and then do some calculation up here that belongs down here. It's very difficult to follow what you've done when you skip around on the page. So work everything in a vertical manner. I advise you can use extra paper. And if you're using extra paper, use engineering calculation paper or some type of grid paper. I don't want lined notebook paper. And then make sure you staple the sheets to the exam afterwards. And each page that you use, make sure it's clear what problem you're working on and where your answer is. Highlight your answer. Block it in, use a colored pen, whatever, but make sure it's real clear what your answer is. And again, if I can't follow your work, I can't give you credit for it. So if your answers are wrong, I'm looking at partial credit. If I can't follow what you're doing, I can't give you partial credit. If the problem calls for a free body diagram, draw the free body diagram. Do not use the original drawing or problem on your page. Draw the free body diagram, including dimensions, all the forces, and the unknowns. And then once this free body diagram is finished and you're going to solve the problem, write the equations that you're using very specifically. Sum of forces in the x equals 0. Sum of forces in the y equals 0. Sum of the moments about point A equals 0. Okay, be very specific, and then follow your calculations under this equation that you've written. Again, it's very difficult to follow work on some exams. Some of you use ink on your homework, and it's pretty spectacular, very neat. Format is very nice. But when you do this on exam and you don't want to use something, you take your ink pen and you are crossing it out. That really is confusing in terms of trying to follow where you're at and what you're doing. So I'm going to recommend you don't use ink so you don't have to cross out work. Okay, so keep that in mind. And again, if you're using extra paper, don't use more than one problem per page. In other words, if you're down here and you finish a problem, then you're going to start another problem, and usually what happens is you can't finish it on that page, you go to the next page. No, I don't want to see that. One problem per page. Okay. Paper's cheap. One problem per page. And again, organize in some logical manner. Don't skip around. On the test page or extra paper. If you can solve a problem you think on the exam, that's fine. Do it. And again, vertical progression. Use a straight edge where appropriate. Make sure you bring a straight edge. Make sure it's legible, so I can give you partial credit. If I can't follow it, you can't get partial credit. So I'm going to run through the chapters, highlight a couple of key points in the chapters, and tell you where the problems will come from. First chapter is on general principles. No problem specifically out of there. It's about units. Again, we're looking at the SI system and our American engineering system of units. So be familiar with that. What is important out of chapter 1 is the fact that we're going to use 3 significant figures for your answers. Sometimes I take off one on homework. I probably haven't been real consistent on that, but I am on the exam, and I do look at this on exams. Every time I see something more than 3 significant figures, I'm going to take off -1. So for each answer that doesn't use 3 significant figures, it's -1. Reason for that is simple. It's false accuracy. We're taking beams and we got loads of 10,000, 8,000, 5,500, and you give me an answer in a support of, 425.32. You're telling me something that's not true. Okay. We're probably measuring out to the nearest 10 pounds, 100 pounds, and you're telling me the answer's in hundredths of a pound. That's not right. The fact that we use units makes significant figures important. Okay, it's not a math. This isn't a math course. We're not multiplying and dividing math problems. We're using units, and this concept of false accuracy is important. Your book uses 3 significant figures. I really agree with that. That's what I've always used too. It's 3 significant figures. So that's the takeaway from chapter 1. Chapter 2, force vectors. We learned about Cartesian vectors, which we'll use in later chapters. We talked about moment of a member, about a point or an axis. Okay. There won't be a specific problem out of force vectors, but some of these principles we use in other chapters. Chapter 3 is particle equilibrium. There will be one problem out of chapter 3. We also looked at pulleys and springs and three-dimensional systems. Okay, so look at the types of problems that we dealt with in chapter 3. Again, probably in two-dimensional space, it's the easiest problem that we encounter. Okay, it's just, particularly if you have pulleys and springs, you need to make sure you do your free body diagrams in there. So that'll be one problem out of chapter 3. Chapter 4, force system resultants. There'll be one problem out of chapter 4. We looked at distributed loads, was introduced in this chapter. We did 2 and 3 dimensions. Key takeaway on the 3-dimensional problems, we learned how to do the moments about a point and moments about an axis system, any axis system. They might review some of these problems. Also, I'll show you which problems to look at or suggest problems for review. So there'll be one problem out of chapter 4. Chapter 5 will have 2 problems. Chapter 5 is, out of all the chapters in statics, this is probably the most important in terms of concepts and how it ties in with many of the other problems that we look at in statics. This is really the key chapter. And one of the reasons for that is that we are able to solve for support reactions. So I've chosen this chapter to take 2 problems. 2 dimensions and 3 dimensions. You probably have one of each if you're thinking about it. The 3-dimensional problems, what you want to do is look for parallel forces to the X, Y, and Z axis. If all the forces are parallel to the X, Y, Z axis, you may be able to solve this using scalar concepts. And I did an example problem and a couple of them, and I think we had a homework problem to look at. Cartesian vectors are important. And the other 3-dimensional problem that I can ask is, can you write the equations to solve this 3-dimensional problem? And it could be, 3 cables with supporting a weight, 3 links supporting some weight or some force acting on this. What are the forces on the links or on the cables? Typically, I wouldn't ask you to solve the unknowns. That could be an extra credit problem, but I would ask you, can you write the 3 equations? And we've done problems, and they're not difficult. Review how you create a Cartesian vector. Unit vectors are important. Okay, and we're using dimensions. Okay, so unit vectors allow you to write a scalar quantity vector, which is the scalar quantity converted to a Cartesian vector. So you may have 3 Cartesian vectors, and included in that would probably be a force in one of the directions. And then the equations, you add all the I components. Say you have 3 unknowns quantities. So you have 3 I components, 3 J components, and 3 K components. You add the I components together, you have an equation. The J components added together, you have an equation. K components you add together, you have an equation. Set the IJK equal to 0, and those are your 3 equations. And you can solve, if you have time to do that. And if you solve for maybe one unknown, I can give you credit, some extra points to do that. If you solve for all of them, probably get more extra credit if you do that. And usually solving involves a substitution. Usually that's going to work out that way. But you don't, if we do this problem, I wouldn't require you to solve, just come up with the equations. So there are 2 problems out of chapter 5. Chapter 6, structural analysis. You will have a problem out of chapter 6. This focused on trusses using the method of joints and method of sections. What you should look for, and again, probably what I would ask in here is going to be a truss problem. Method of joints, usually. We do have frames. I won't ask a frame problem specifically in here. I could put a frame in as an extra credit problem. So the problem here will be the truss, and it'll be the method of joints. Again, check your reactions. If your reactions are wrong, the solution to the truss is going to be wrong. Know how to identify zero load members. It could come in handy. Understand what symmetrical loading is and how to identify it. Makes it simplifies greatly a solution. If it's symmetrical loading, we know we can just add the loads together, total. The reactions divide by 2, you get the reactions. Okay, so total load divided by 2. And then you're only having to solve for half the truss, because that line of symmetry, what's on the left line is going to, left of the line is going to be the same as on the right. So you just solve half, and then you mirror it on the other half. Okay. And this one won't be as extensive as what we had on the exam. And just keep all these in mind as you look at the truss problem. I insist you label the force on the truss. If it's not, I will take some points off. It's extremely, and on the exam, most of you didn't do it. And I was very specific when we solve these problems that you need to label the forces on the truss. It's very difficult to go look at your work and find an answer to a member in all the work that you've done. Okay, so label the forces that you solve for on the truss. 12.5 newtons tension, 12.5 newtons compression, whatever. Label it on the truss member. That way I can very quickly see if you've done it correctly. I could grade it in 30 seconds. But more importantly, if I see a truss member that's incorrect, I know where to go in your joints that you're down here solving, and I can see what you did wrong. It may have been just a sign, not a big deal, okay, which makes everything else wrong. So this is important. Label these. Okay, make sure you check your reactions also. So 1 problem out of chapter 6. Chapter 7, you'll have 1 problem. Shear moment diagram. Okay, we just did that. Probably won't have you do shear moment in a section since we're doing the diagram. May ask you to write an equation in there in one of the sections, that type of thing. Make sure you have your straight edge to do this. And reactions are correct, obviously. Draw your diagrams underneath the given beam. Don't draw something off to the side. And friction, won't be this could be a extra credit problem here. Usually it's just solved summing forces, the x and y, and maybe a moment equation. So if I give you a friction problem, it'd be a extra credit problem. So the one problem will be shear and moment diagrams. The best review are your 4 exams, and I have the solutions posted. So look at the problems, exams 1 through 4. And then I suggest you review the problems we worked in class. Work for you in class. It's probably the best way to review. And you can look at your homework problems and you've done enough, right? You've done enough. You solved all of your homework problems, correct? Yourself. Yeah, sure you did. It's the best way. And again, if you're looking at exams or you're looking at a problem I worked in class, don't just look at how it was solved. Draw the whatever it is you're looking at, the structure, the beam, whatever we're solving. Draw it yourself and solve it without looking at the solution. The only way to learn a problem is to solve it yourself. Okay, you can look at it and say, yep, I understand that. I can work in class, say, yep, I understand that. Look in your textbook, you see how they do it. Yes, I understand that. But can you take that same problem and do it yourself without looking at the solution? That's the key. And I encourage you to take some time in this next week and work a few problems on your own. Number one, it builds your confidence that you know how to do it. You don't sit there and panic. And that's probably the most important thing. And I guarantee you, and some of you probably know this, if you can't solve the problem on your own, you won't solve it on the exam. Okay, so if you can't solve it while you're practicing and studying, you can't solve it on the exam. So make sure you do this. I want you all to be successful on the final. I know you got a bunch of finals coming up in other classes. Wish you well. Take time to enjoy life, obviously, but work. This is a critical time, are your final exams. So good luck to all. If you have any questions, send me an email. And again, I've got some homework stuff I need to finish up, so I will do that. But if you have any questions, send me an email and I'll respond.